Please confirm whether audio video is clear. Just confirm audio video is clear to you. Just confirm whether audio video is clear to you or not. Just confirm it once. Audio video is clear. Audio video is clear to you. Just confirm me once. Okay. So a very good morning everyone. I welcome you to the foundation course by IMS GATE Academy. Myself Prateek Mishra, and we are conducting this course for strength of material. The purpose of this course is to give you the basics that can be used to solve complicated and application based questions that are directly asked in GATE examination. So we started discussing with shear force and bending moment diagram, and in the previous two sessions we have seen how to draw the shear force diagram and the bending moment diagram. Today we will going to discuss all the standard cases which are there for a simply supported beam and a cantilever beam for drawing the shear force and the bending moment diagram. Okay, so we will start with a simply supported beam eccentrically loaded. So case 1 is simple. We will start with a simply supported beam which is loaded eccentrically. So this is our simply supported beam, and this simply supported beam is of length L, right? And the point load is applied at a distance of A from left end at a distance of B from the right end. The total length of the beam is L. This is L. This total length is L, right? We need to draw the shear force and the bending moment diagram for this beam. So the first step in drawing the shear force and the bending moment diagram is to find the support reaction. So step number 1 is clear to us. Step 1 is find support reaction. Find support reaction. Find support reaction, right? So first is, I will name this as point A and this one as point B. For support A, it's a hinge support, so I have RA and one more load, one more horizontal reaction HA. And for B, I have one vertical reaction RB, right? Now, as soon as you look into the beam, first thing you should decide whether the loading is happening in vertical direction or any load is happening in the horizontal direction. If the loading is only happening in the vertical direction, then in that case this horizontal reaction will be 0. And in the 80% of the cases that are asked in examination for a simply supported beam, you will not find any loading in the horizontal direction, right? But still, this gives us a practice of considering HA, because sometimes what happens is when some inclined load is given, okay, there we ignore this HA unnoticingly, right? We ignore this HA even we don't know that, right? It's a very silly mistake that we usually do. So make it a practice. Whenever there is a hinge support, make two support reactions. it doesn't take much time if you just take the summation of horizontal forces 0 and make HA 0, right? This will make you or give you the clarity that HA will always be present. No doubt its value will be 0 when vertical loadings are there. Okay, so step number 1 is summation of horizontal forces 0. So from here, only one horizontal reaction is there, HA, and no other horizontal reaction is there. Therefore, HA is also 0. Next, I'll take summation of moment about point B to be 0. So for about point B, the first moment will be due to RA, and this is the clockwise moment. So moment of RA is RA into L, and this is the clockwise moment. So I will write RA into L. The second moment will be due to this point load, and this will be a anti-clockwise moment. Moment due to this point load about point B is P into B. So minus P into B is equal to 0. From here the value of RA comes out to be PB by L. This is the value of RA. Okay. Similarly, we can calculate the value of RB also by taking the moment about point A to be 0. If I take summation of moment about point A to be 0, so the first moment will be due to this load P, and this load P will going to give a clockwise moment about this point A. Moment due to this point P about point A is P into A, and this is a clockwise moment, hence positive, right? Next moment will be due to this RB, and RB into L will be the moment about point A, and that will be an anti-clockwise moment. So minus RB into L, and this should be equal to 0. So from here the value of RB comes out to be PA by L. PA by L. So this is the value of RA and RB, right? Now, for drawing the shear force diagram, we need to write the shear force equation for two span. This is for span AC and then for span CB. This is point C. So first we write a shear force equation for span AC, and then we write shear force equation for span CB. Or we can even directly draw the shear force diagram because it is a case of point load. One thing we know that between that span or in between that span where no loading is present, there the value of shear force will always remain constant, right? So let us draw the shear force diagram first. So here I have a simply supported beam. Here I have a simply supported beam like this. For this simply supported beam, one eccentric load is acting P, and this load P is at a distance A from end A and B at a distance of from end B, ABC, right? This is my beam. Now let me draw the shear force diagram. For suppose the value of RA is the value of here, the reaction is, the value of reaction is PB by L. The value of reaction is PB by L. Here the reaction is, this reaction is PB by L, and this reaction is PA by L. So clearly we can say that this PB by L is more than PA by L. We can also say this because this load is more towards A end. Therefore, more amount of reaction will be developed at end A, right? So if I need to draw the shear force diagram, at point A, I need to move up by the amount of PB by L. This is PB by L. This is your PB by L. This is PB by L, right? From A to C, since there is no load, therefore shear force diagram will be constant like this. This is from A to C. Since there is no load, so shear force diagram will be constant, okay? Then at point C, you have a point load acting in the downward direction. So you have to move down by the amount of P. So this displacement or change of ordinate is P. This change of ordinate is P, right? This change of ordinate is P. This entire change of ordinate is P. The first part is PB by L. So therefore this is equal to P minus PB by L. So just do this. P minus PB by L. This is this part which is below the line, right? So when you do this, you will find that P into L minus B by L. And L minus B is nothing but A. So you have PA by L. So this lower part is PA by L. So this point is minus PA by L. And then from C to B, since there is no load, so shear force diagram will be constant like this, right? And at point B, you have an upward load of PA by L, and this is also PA by L. So you need to move up by the amount of PA by L, which closes the shear force diagram like this. So this is plus, this is minus, and this is minus PA by L. So this is how you draw the shear force diagram. This is your shear force diagram. Now drawing the bending moment diagram, okay. So for drawing the bending moment diagram, we need to know the equation of bending moment for span AC and then for span CB, then only we can draw the bending moment diagram. So first of all, let me calculate the equation of bending moment for span AC. So for span AC, if I consider any section XX in span AC, this is my section XX. So I will look towards the left of this section. When you look towards the left of this section, only one support reaction is there, and that support reaction is giving the sagging moment. And how it is giving? If you just hold this beam and allow this load to act in the upward direction, this beam will sag like this. This beam will have this kind of tendency, right? And this is the sagging moment. And this is the sagging moment, where the lower fibers are in tension and the upper fibers are in compression. So this moment due to RA will be the positive moment, right? So I will write bending moment at section XX is equal to RA, and RA is PB by L, PB by L multiplied by the lever arm, which is X. So this distance is X. This distance is X, right? This is the lever arm, which is X. So I'll got the first equation. That is bending moment for span AC is PB by L into X. Now this is the equation of straight line with a positive slope, okay. Now moving to span CB. For span CB, again I'll consider any section XX. This is my section XX, and this section XX is again at some distance X from my left hand, okay. Now in order to write the bending moment equation at section XX for span CB, you have to clearly observe there are 2 point load. First one is this RA. This RA is again giving the sagging moment, and this sagging moment is a positive moment, right? So for span CB, for writing the bending moment at section XX, so bending moment at section XX is equals to moment due to RA, and this is a positive moment, so this is PB by L into X, okay. Then next moment will be due to this load, and this load will going to give the hogging moment like this. This load will going to give me the hogging moment. This load will depress the beam in the fashion I have drawn, okay. So this P will going to give me the hogging moment, and moment due to this load P will be minus P into this distance. Minus P into this distance, and this distance is nothing but X minus A. This distance is nothing but X minus A. This distance is between this load and this section, this distance is X minus A. So lever arm is x minus a, load is P, and that is hogging moment. So P into x minus a. Okay. So this is the bending moment equation for span CB. Just solve it some more. So you have PB x minus PLX minus PLA divided by L. When you take P and X common, right? When you take P and X common, you have B minus L in the first two terms. So you have P and X common. So you have B minus L in the first two terms and minus PLA divided by L. This B minus A is nothing but, B minus L is nothing but minus A. You can also write it as L minus B with a minus sign. So I'll just solve this further. So bending moment at section XX for span CB is minus PLA divided by L, and then this term minus PXA, because this is minus A, minus PXA divided by L. So you can take minus PA by L common. So you have minus PA by L common, and in bracket you have L minus X. So this is the bending moment at section XX for span CB, right? Again, this is a straight line equation with a negative slope. So if I draw the bending moment diagram for this beam, so this is my beam AB. This is my beam AB, right? This is A, this is B, A, B, and this is point C. So when I draw the bending moment diagram, first of all, at point A, the value of bending moment is at point A. So when you look into this equation, right, this is for span AC. So at point A, the value of X is 0. So when you substitute X is equals to 0, you will find bending moment is 0 at point A. Then when you look for span AC, this is the straight line with positive slope of PB by L. Okay. So for span AC, you have this straight line with a positive slope of PB by L. At point C, the value of bending moment is, at point C, the value of bending moment the value of bending moment will be PB by L into A, because at C, the value of X is A. So the value of bending moment at C is PAB by L. So this is PAB by L, right? Then when you look for span CV, this is the bending moment equation. And this bending moment equation is a straight line equation with a negative slope. Okay. This straight line equation with a negative slope. When you take minus common, this will be L plus X. So this will be like this. And this is a positive bending moment diagram. This is a positive bending moment diagram. BMD. A, B, C. So I hope you understood this very clearly, and I think you don't have any doubt in drawing the shear force and the bending moment diagram for such a simply supported beam which is eccentrically loaded. Okay, from this question I want you to remember one thing, only one thing. When you have calculated the support reaction, okay, for suppose you have calculated the value of RA. So RA is nothing but load into this distance divided by L. And for calculating RB, RB is this side. So you have to take load multiplied by A divided by L. Because this direct formula will help you to calculate the support reaction when n number of loadings are there. Okay, what I've told you? If you have to calculate the value of Ra, take this load multiplied by this distance divided by L. Similarly, when you have to calculate Rb, you take load multiplied by this distance divided by L. This will directly going to give you the formula. Means directly going to give you the value of support reaction without even applying any equation. So if you remember this simple formula, it is very easy to calculate the support reaction. Yesterday we did one question for support reaction. There we have applied the moment equation and then we have also applied the sum of vertical forces 0, right? So you need not to do that. Yesterday I haven't told you that because we haven't discussed about this relation. How to calculate the support reaction using the direct formula. So the first thing you should remember for calculating the support reaction is, if you have to calculate Ra, Ra is load multiplied by the other distance divided by L. And if you have to calculate Rb, it is load multiplied by this distance divided by L. Right? I'll give you one quick question, you try and solve this. I'll give you one quick question and this quick question is like this. For suppose you have this load of 5 kilonewton, then you have this load of 6 kilonewton, then you have this inclined load of 10 kilonewton and this inclination is 30 degrees, right? And you need to calculate the support reaction for end A and end B. Okay. So first of all, when you look at support A, you will going to have two support reaction. This is Ra and Ha. And when you look to support B, it has only one support reaction, Rb. Okay. The first thing is you should check whether all the loadings are happening in the vertical direction or is there any loading in the horizontal direction also. So when you look into this inclined load, the horizontal component of this inclined load will going to give the support reaction Ha. So the first step is Ha is equals to that 10 cos 30 degrees. And this is in kilonewton. Done. First Ha is done. Right. Now we will calculate Ra and Rb using that simple trick or formula that we have. So for calculating Ra, I need to give you these distance. All these distances are 3 meters. All these distances are 3 meters. This is 3 meter. This is also 3 meter. All these distances are 3 meter. The total length of the beam is 12 meters. Okay. Now for this 5 kilonewton load, the component of this 5 kilonewton load on Ra will be 5 into this distance. That is 3 plus 3 plus 3, 9. Divided by the total length, which is 12. So the component of 5 kilonewton on Ra will be 5 into 12 divided by, 5 into 9 divided by 12. So Ra is 5 into 9 divided by 12. This is the first. Okay. Now look into the second load, 6 kilonewton. For this 6 kilonewton load, the component of the 6 kilonewton load on Ra will be 6 into this distance, that is 3 plus 3, divided by the total length, 12. So plus 6 into 6 divided by 12. Next is this 10 kilonewton load. So when you take the vertical component of this 10 kilonewton load, it will be 10 sine 30. This will be 10 sine 30. This will be 10 sine 30 degree, right? And for this 10 sine 30 degree, this distance is 3 meter. So 10 sine 30 degree into 3 divided by 12, and that will be the component of this 10 sine 30 degree on Ra. So this is 10 sine 30 degree into 3 divided by 12. Okay, just try for Rb, and I'll be back in 1 minute. Okay, so we were discussing how to calculate the support reaction. So RA we have calculated. It is load of 5 kilonewton multiplied by this distance divided by the total length. Then this load of 6 kilonewton multiplied by this distance divided by the total length. So 6 into 6 by 12. Then you have the vertical component of 10 kilonewton load, that is 10 sine 30 degrees, and 10 sine 30 degrees multiplied by this distance of 3 meter divided by the total length of 12, right? Similarly, when we calculate RB, we will take components of loads one by one. So first of all, for calculating RB, we have this 5 kilonewton load. So component of this 5 kilonewton load on RB will be 5 kilonewton load multiplied by this distance, that is 3 meter divided by the total length, which is 12. So 5 into 3 divided by 12. Similarly, take this load of 6 kilonewton multiplied by this distance, which is 6 meter divided by the total length, which is 12. So plus 6 into 6 divided by 12. When you take the next load of 10 kilonewton, the vertical component is 10 sine 30 degrees. 10 sine 30 degree multiplied by this distance. This is 3 plus 3 plus 3, 9 divided by total length, which is 12. This 10 sine 30 degree into 9 divided by 12 will be the component of RB. So plus 10 sine 30 degree into 9 divided by 12. So this is the component of RA and RB, and this is how you can calculate the support reaction using one single step. Okay, this is also known as the principle of superposition, where you simply add the effect of all the vectors. Okay, in order to get the total value of this vector, you add the effect of all the vectors. We know that force is a vector quantity. Okay, so either you can understand in terms of principle of superposition, or you understand in terms of component. That is, for every transverse load, there will be the component of RA and there will be the component of RB. Okay, so this is how you can deal with the complicated beams for calculating the support reactions. Okay, now moving on with this, case number 2 is for drawing the SFD BMD. Case number 2 is simply supported beam loaded with UDL. So simply supported beam with UDL, right? So this is my simply supported beam, and for this simply supported beam, it is loaded with UDL. So this is W kilonewton per meter. And we need to draw the shear force in the bending moment diagram. Again, for this beam, step number 1 is simple. Calculate the support reaction. So first of all, this is my point A and this is my point B. This support reaction is RA and this one is HA. This support reaction is RB. The first thing is we need to calculate RA and RB, okay, and HA. This UDL is acting in the vertical direction. So there is no component in the horizontal direction. So the value of HA will be 0. So if you take the summation of horizontal forces, 0, from here you will get the value of HA equal to 0. Then stand at point A, right, and take the moment of this UDL and this RB about point A. So summation of moment about point A should be equal to 0. I have already told you in the previous session, whenever UDL is acting, the total load will be W into L, W into this length L of the beam. This is the total load. And this total load of W into L will be acting at the CG of this UDL. And this CG of the UDL can be imagined as, first of all, imagine this as a rectangle. So the CG of this rectangle will be at the midpoint. So this total load of UDL, W into L, will be acting at the midpoint. It will be acting at this midpoint. It will be acting at this midpoint. So this total load of W into L will be acting at this midpoint, right? And this distance is L by 2. This is L by 2. So other half will also be L by 2. So first of all, write down the moment about point A, and the moment about point A should be equal to 0. So there are two loads causing the moment about point A. First one is this UDL, and this UDL will cause the clockwise moment, hence taken as positive. So for UDL, the total load is WL and the lever arm is L by 2. So moment due to UDL, WL into L by 2. This is the moment due to UDL. Second one, moment due to this RB is, it is acting or giving the anti-clockwise moment. So RB into L will be the anti-clockwise moment. So minus RB into L should be equal to 0. So from here the value of RB comes out to be okay, is it visible? So if you observe this loading carefully, this is a symmetrical loading. So either you use these equations and calculate the value of RB on RA, or you can directly just focus on the loading. This loading will be symmetrical. So half and half of this loading will be distributed to RA and RB. So directly you can write RA is WL by 2 and RB as WL by 2. The another method is take the moment about point A to be 0. There you will get the value of RB as we have already calculated. Second is take the moment about point B to be 0. From there you can get the value of RA, or directly you can write RA is equals to RB is equals to WL by 2. So this is WL by 2 and this is also WL by 2. So we got the support reaction. The next thing is we need to write the shear force equation. So this is the UDL which is acting over the beam. This is W kilonewton per meter. Now consider any section XX from the left support. Consider any section XX from the left support, right? This is section XX from the left support and this is at some distance X. Okay. First of all, the total amount of load that is acting due to UDL on this span is X into W. So W into X is the total amount of load, and this W into X of this UDL will be acting at the CG of this UDL, that is at a distance of X by 2. This is at a distance of X by 2. This distance is X by 2. This distance is X by 2, right? So this load of UDL which is acting on this span of distance X, the value will be W into X, and this W into X will be acting at a distance of X by 2. So shear force equation or shear force equation at section XX, first of all, you have this WL by 2, this is RA, and this is acting in the upward direction, so plus. So WL by 2, this is plus. Then you have minus W into X, this load, minus W into X. As you can clearly see this is the equation of straight line with the negative slope of minus W. So if I need to draw the shear force diagram for this beam, it will be very simple to draw. First, at this point, you have an upward load of WL by 2 acting. So I have to move up by the amount of WL by 2. So this is WL by 2. I have to move up by the amount of WL by 2. Then there is the straight line with the negative slope of minus W. So this is the straight line with a negative slope of minus W. Then at this point, I have to again move up by the amount of WL by 2 due to the support reaction at B. So this is minus WL by 2 This is plus WL by 2 and this is plus and minus, and this is the shear force diagram. Even if you substitute the value of x as L, at x is equals to L here, the shear force at distance L is WL by 2 minus WL. So this comes out to be minus WL by 2. So from here also you can calculate the value of shear force at this point is minus WL by 2. And at this point you have an upward acting support or load of WL by 2. So you have to move up by the amount of WL by 2. And this is how you can draw the shear force diagram. Okay. So this is the shear force diagram. Now for the same beam, if I need to draw the bending moment diagram, first I need to write the bending moment equation. So bending moment at section XX. So for when you stand at section XX, this load of WL by 2 will give me the sagging moment. So this load WL by 2 multiplied by the lever arm will be the moment, and this will be a sagging moment. So WL by 2 into X, this is the first moment. Second moment will be due to this UDL. The total UDL is W into X, and this W into X will be acting at the CG of this UDL, and the lever arm will be X by 2, right? This CG of this UDL will be at a distance of X by 2 from this section XX. So this is W into X by 2 will be the moment due to this UDL, and this will be a hogging moment. So W into X by 2, this will be the moment due to UDL, right? And this is a hogging moment. This will try to hog the beam like this. This will try to hog the beam like this. So when you just do the calculation, you will have WLX by 2 minus WX square by 2. So when you observe this bending moment equation carefully for section XX, it is clearly visible that this is the downward opening parabola, because the value of the coefficient of x square is negative. Therefore, it is a downward opening parabola. Just quickly get me the value of bending moment at different points. First, get me the value of bending moment at x is equals to 0. So when you substitute the value of x is equals to 0, the value of bending moment will be 0 minus 0. So at this point, at this left end, the value of bending moment is 0. Second is, at x is equals to L, get me the bending moment value. So at x is equals to L, the bending moment value is W into L by 2. So this will be WL square by 2, first term. Then minus WL square by 2 is the second term. So WL square by 2 and WL square by 2 will going to cancel out. So the value of bending moment at this point is again 0. So at the starting point and at the finishing point of the beam, the value of bending moment is 0. This can also be understood by looking into the beam. When you look into the left side of the beam or the hinge support, here the moment is 0. And also for the roller support, the moment resisted is 0, right? So for both the ends, the bending moment will be 0. And this we have proved through equation also. So this is the upward downward opening parabola. Now plotting this. So you have this. You have this beam. Over this UDL is acting, and the intensity of UDL is WL by WL. W kilonewton per meter, sorry. In order to plot the bending moment diagram, this bending moment diagram will be the downward opening parabola. And this is how the downward opening parabola looks like, right? This is the downward opening parabola. Now we need to find out the point where you will get the maximum value of bending moment. This is bending moment maximum. And we need to find out this point and also the value of maximum bending moment. So the basic process for doing this is do d by dx of bending moment equal to 0. So first of all, bending moment equation is WLX by 2. So this is WLX by 2 minus wx square by 2. This is the bending moment equation. In order to get the maximum bending moment, d by dx of Bm should be equal to 0. So d by dx of Bm should be equal to 0. So when you do the d by dx of bending moment, you will have d by dx of WLX by 2 is, I'll write here, d by dx of WLX minus WX square by 2. This should be equal to 0. So when you do the d by dx of WLX, it will be WL, and d by dx of WX square by 2 will be 2WX by 2. So this be W into X, right? 2 and 2 cancels out. And this should be equal to 0. So from here, when you calculate the value of X, X comes out to be L by 2. So at the midpoint, you will get the maximum value of bending moment. So this distance is L by 2. This distance is L by 2. Now, what is the maximum value of bending moment? So just substitute X is equals to L by 2 in this equation and you will get the maximum value of bending moment. Okay, so bending moment maximum, Bm max. So in that equation, in this equation, substitute X is equals to L by 2. So when you do that, you have WL square by 4, WL by 2 into L by 2. So this will be WL square by 4. Next one is minus W by 2 into X square. And X square is L square by 4. So this will be WL square by 8. So minus WL square by 8. So when you do the quick maths, WL square by 4 minus WL square by 8, this will be WL square by 8. This will be WL square by 8. So the value of maximum bending moment is WL square by 8. This Bm max WL square by 8. Right, this is the value of maximum bending moment, and this maximum bending moment is positive. This is your BMD, right? So anytime in any question, if you need to find the value of maximum bending moment, you need to go for this simple straight procedure only. You have to differentiate the equation of bending moment and equate it to 0. And then from there you will get the value of X, where you will have the maximum value of bending moment, right? Okay, now moving on with the cases of cantilever beam. So this is case 3. Cantilever beam subjected to point load at free end. So this is my cantilever beam like this. And this is the point load P, which is acting at the free end. Okay. Now calculating the support reaction is very easy for cantilever beam, as you have, if I name this point as A and this point as B, your RB will be RA, not RB. Your RA, that is support reaction at A, should be equal to this load, because when you take the summation of all the vertical forces to be 0, you will get RA is equals to P. Similarly, when you take the summation of all the horizontal forces to be 0, since there is no horizontal force, so HA is also 0. So HA is also 0. This HA and this HA is 0, right? Because there is no horizontal force. Now we know the support reaction. So support reaction is through summation of vertical forces 0. So RA is equal to P, right? Now, how to draw the shear force diagram for this beam? So the first thing is, consider the section XX. This is my section XX. And for this section XX, I have to look towards right. Okay. I'll just recall the sign convention what we use. For shear force diagram, if this is my section XX, right? So any load which is acting upwards on the left of the section and downwards on the right of the section is taken as positive. Just remember this, okay? Because this will not create any confusion. Just remember this. Any load on the left upward is positive, and on the right, if it is downward, it is negative. So here what we are considering the right of the section. And when you look towards right of the section, this load is coming downwards, hence will be drawn as positive in the shear force diagram. Okay. So when I draw the shear force diagram, if I draw the shear force diagram for this beam, at this point, I have to move up by the amount of P. I'll move up by the amount of P at this point because this P is positive on the right side. Then there is no load acting between point B and point A. So shear force diagram will be constant like this, right? Then this RA is acting upward, and we are on the right of the section. So we have to move down by the amount of RA, and that is equal to P. So this is my shear force diagram, and this is positive. This is the shear force diagram, and this is positive. You can also draw the shear force diagram by standing at point A. So at point A, if you look into the right of this section, if you look into the left of this section, standing at point A, there is an upward reaction force RA. So you move up by the amount of RA, and this RA is equal to P. Then from RA to point B, there is no load, so shear force diagram will be constant. Then at point B, you have to move down by the amount of P. So this closes the shear force diagram, okay. Now, drawing the bending moment diagram. Every time for a cantilever beam, for drawing the bending moment diagram, you have to start from the free end. You have to always start from the free end. And sign convention is same for bending moment. If the load is giving the hogging moment, it is negative. And if the load is giving the sagging moment, it is positive. Okay. Now drawing the bending moment diagram. So bending moment diagram for this beam. So if you look into this cantilever beam, this load is P, right? This is point A and this is point B. This is my section XX. And the distance of the section XX from end B is X, right? If you stand at this section XX, this point P is trying to move the beam downwards. And this beam will hog like this. This beam will hog like this, right? So this load P is giving the hogging moment. And the value of this hogging moment at this section is P into X. So bending moment at section XX is P into X with a minus sign, right? This is the value of bending moment, and this is negative. You keep on increasing the value of moment till point A, and at point A, you will have this support moment MA. And this support moment will be equal to this moment due to this load. And MA will equal to P into total length of the member, L. So this MA is P into L, and that will pull the bending moment upwards, right? So if I draw the bending moment diagram, at this point B, bending moment is 0, and this over this span of length L, your bending moment equation is minus P into X. So you have to move like this, minus P into X like this, right? At this point A, you have the resisting moment MA, whose value is P into L. As you clearly state here, when you calculate the value of bending moment, this is minus P into L. and this moment will try to pull. This moment is the resisting moment, and this will try to pull the bending moment diagram upwards, right? So this is negative. So this is your bending moment diagram. Just 1 minute. Okay, so for this, we haven't calculated the support reaction. For the support, you have three reactions, RA, HA and MA. In order to calculate MA, so MA is MA plus this moment, or MA should be equal to the moment due to this load. So MA is equal to P into L. So this is the third support reaction, MA. This MA is P into L, and this MA will change the ordinate of the bending moment diagram directly and will close the bending moment diagram, right? So first of all, if there is any point load, that point load never changes the ordinate of the bending moment diagram, right? As you can clearly see here that this point load is acting at the free end, but at this free end the bending moment is 0. So bending moment will not change the ordinate of the bending moment diagram, but if there is any concentrated moment, it will going to change the ordinate of the bending moment diagram. So you can clearly mention this note point. Point load will not change the ordinate of the bending moment diagram, right? So you can clearly remember this. Chalo, moving to the last case for drawing the SFD and BMD, we will going to see how to draw the SFD and BMD for a cantilever beam subjected to UDL. So last case is, case 4 is cantilever beam subjected to UDL. So this is W kilonewton per meter. So step 1 is again same. You need to find the support reaction at A. So this is your end A and this is end B. At end A you have three support reaction, RA, HA and MA. Right? These are the three support reaction. When you take the summation of horizontal forces 0, your HA is 0. When you take the summation of vertical forces 0, you will get the value of RA, and when you take the moment about point A to be 0, you will get the value of MA. Okay. So first of all, I'll write summation of first point is summation of horizontal force is 0. So from here you will get the value of HA is 0. Second, when you write summation of vertical force is 0. So from here you will get RA is equals to total load. Total downward load is W into L. L is the length of this beam. So total load is RA is equals to W into L. Now third one is calculating the value of MA. So summation of movement about point A should be equal to 0, right? So this load will be giving the clockwise moment. So this reaction moment should be anti-clockwise moment. So minus Ma plus this total load W into L, and this total load will be acting at the CG of this load, and at the CG of this load will be at a distance of L by 2. So the moment due to this UDL will be W into L total load multiplied by L by 2, which is the lever arm. So this is WL into L by 2, and this should be equal to 0. So from here the value of Ma comes out to be WL square by 2. This is the value of Ma, Ra and Ha. Okay. Now write the bending moment equation at section XX from the left support. Okay. Before that we need to write the shear force equation. First of all we need to draw the shear force diagram. Okay. So shear force at section XX, and this is my section XX, this is my section XX, this is my section XX, right? So we will draw through the left side only. We will consider the left side for drawing the shear force diagram. Okay. So when standing at point A, right, standing at this point, you have to move up by the amount of Ra. So Ra is WL. So I'll move up by the amount of Ra, that is W into L, right? Then this UDL will give the slant line to the shear force diagram. So shear force diagram keeps on decreasing like this. This is the shear force diagram for SFD for this cantilever beam over which UDL is there, right? Even if you write the shear force equation, so shear force equation for this distance x, so what it will be? It will be Ra, and Ra is how much? Ra is WL, right? Minus this load, and this load is W into X. So clearly this is a straight line equation with the negative slope of minus W. So this is minus W. The slope of this line is minus W. This we have already seen when we were drawing the shear force diagram for the first time. I have told you there, whenever UDL will be acting over the beam, there the shear force diagram will be an inclined line with a slope of this load intensity, right? So the slope of this line is minus W. Okay. So this is how you draw the shear force diagram for this beam. Now drawing the bending moment diagram, BMD. So again I consider this beam. For this beam, this is the UDL, right? This is point A, this is point B. This total length is L. Now I consider this section XX, and every time I have to draw the BMD, I will look into the right side of the section. Now this distance is X. I will look into the right side of the section. Okay. On the right side of the section, what will be the bending moment at this section XX due to this UDL? First of all, this UDL will try to hog the member like this. Right? So that will be the negative bending moment. So bending moment at section XX, first thing is it will be a negative bending moment. Second, what will be the value of bending moment? The value of bending moment is this load W into X, this total load W into X, right? This total load, and this total load will be acting at the CG of this load, and the CG of this load will be at a distance of X by 2 from this section XX, right? So lever arm will be X by 2, total load is W into X, and this is giving the hogging moment. So the moment due to this UDL at this section XX is W into X by 2 with a minus sign. So this is minus WX into X by 2. So this is minus WX square by 2. So bending moment at section XX is minus WX square by 2. Clearly at X is equals to 0, the value of bending moment is 0. at x is equals to 0, the value of bending moment at point B, this is point B, bending moment is 0. And when you substitute x is equals to L, you will get the value of bending moment at the point which is just right of this support A. So bending moment at x is equals to L, at x is equals to L, bending moment at A is WL square by 2, right? And this is minus WL square by 2. So in order to plot this bending moment diagram, so again, this is a parabolic equation and with a minus sign, so it is a downward opening parabola. So this can be drawn like this, right? Starting from 0, it can be drawn like this. So this is my downward opening parabola with a minus sign. At just towards the right of this support, the value of bending moment is minus WL square by 2. And at this point A, you have the counterclockwise moment acting that will complete the bending moment diagram. So you need to move up by the amount of WL by 2 because this support reaction will going to hog the beam, right? This support reaction is acting like this, so it will hog the beam like this. Sorry, it will going to sag the beam like this, and sagging moment is positive. Therefore, we are moving up by the amount of WL square by 2. So this is minus WL square by 2. This is minus WL square by 2, and this bending moment diagram is negative. This bending moment diagram is negative. Right? So this is how you draw the bending moment diagram for all the standard cases. It can be a simply supported beam or it can be a cantilever beam. So I hope in today's session you got a lot of information about how to draw the shear force and the bending moment diagram for a simply supported and a cantilever beam. For a cantilever beam, always keep this in mind. Whenever you are drawing the bending moment diagram, always start from the free end. And you have to check whether the loading is giving the hogging moment or the sagging moment. If the loading is giving the sagging moment, the bending moment will be positive. And if it is giving the hogging moment, it will be negative, right? So I hope you find this information very useful and it may also help you to solve the complicated and the application based question asked in the GATE examination. So this is all for today. We'll continue tomorrow, same time, same place at the YouTube platform of IMS GATE Academy. And from tomorrow, we will going to start with the bending stresses. So thank you so much for listening patiently. Have a great day ahead. Thank you so much.